Michael and I worked on. It was fast Laplacian solvers. So that project was masterminded by Richard Peng, who actually introduced Michael and me in an academic context. We've met a couple times before at Facebook and at various programming competitions, but this is the first time we actually sort of got to talk and work over a longer period of time. The project was about trying to just take the current fastest Laplacian solver, which was at the time due to Kudis, Miller, and Peng, and try to make it faster. And Richard had a pretty clear vision of how to do it, even sort of over a year before before we actually got the result. And it was divided into two parts, where we had to work on some combinatorial properties of graphs, and we had to work on linear algebra and optimization. And that was Michael's last year of undergrad at MIT. So it was actually, I think he started working on it a bit before the summer, before his last year of undergrad. And for me, it was right about the start of my PhD at Carnegie Mellon. So we started talking while I was still in Poland. And we collaborated remotely on faster low search spanning trees, which were a tool we used for Laplacian solvers. We got a result there together with Gary Miller and Shenzhen Xu and Richard. And then we spent some time working on this problem and looking forward at CMU, where Michael was visiting Gary for the summer. Actually, I remember Michael's office at CMU. So he was given an office for visiting academics. And it wasn't a very nice office. You know, it was sort of this small thing with no windows. But Michael really found one very nice property of it. So he was very happy with the office. So know that Michael really thrived when talking to people. He really found that stimulating and enjoyed it very much. And he really liked talking to Gary. They really had an amazing connection. The problem was that Michael's office was on the 6th floor, and Gary's office was on the 8th floor, and so it was problematic to see if Gary was around. But actually, there was a big open space in CMU. So let me draw a picture. So Gary's door were here. There was a balcony here, and then there was this painfully long staircase here, and an open space here. So essentially, if you wanted to see if Gary was in, you could just see whether his door was open, because Gary always keeps his door open when he's in the office. But the problem was you couldn't really do this from this open area here, right? Because you would stand here, and you would not be able to see whether the door open. So Michael's office was here. So I saw multiple times Michael get out the key and walk into his office and walk right back to his desk, where he could easily see from his chair whether Gary was in. So I found it really funny. Yeah, so let me say a bit about the problem we worked on. So I won't talk too much about the whole problem. I will tell only about the issue that really took us, I would say, all the time after we have, or at least on the second part of the paper that we worked on together with Richard, Rasmus and Anuprao. Okay, so the basic approach for the problem was to just to solve linear systems on graphs using preconditioned iteration based on with the preconditioner being a sparsified version of the graph. So the basic idea would be you would have your current solution x, and you would replace it with right. So this is essentially, so if H was identity, right? So if you had a simple, if you use no preconditioner, that would be just gradient descent, and here it's just gradient descent with on H inverse L, which we hope to be well conditioned. So if you, so the typical way to proving these things work is you take the, so let's say you're looking for the optimal solution x dash. So you'll typically be bounding the distance between your current solution and x dash in L norm. Okay, and if you know that the condition number of H relative to L is actually low, so you actually have a good preconditioner in the classical sense, then this is actually very easy to prove. You just write this out, and you will get some terms that look like that will say that sort of your next. So let's say this is I plus 1, or maybe t plus 1. That would say that your next distance looks somewhat like the previous one. Minus, and now you will get some terms that look at H inverse. So the bulk of your reduction will be here. You will get something like and then you'll get a similar term, and you'll get 1 alpha here, plus alpha squared times a similar term with H inverse, LH inverse. I won't do the full computation here. But essentially, if you know that H and L are closed, then these terms are pretty easy to bound. And Richard's, okay, and also the way we actually obtain this sparsifier H in previous algorithms is we take a low-stress spanning tree of the graph, which is essentially a graph that has the property that let's say any remaining edge of the tree has low stretch with respect to it. Uh, and then we sample a bunch of additional edges and add them to that preconditioner. So then if you sample enough edges through matrix contrastation bounds, it's pretty easy to show that H is actually spectrally close to L, and these things become very easy to bound. So Richard's idea was that maybe because of the way we construct this preconditioner, we don't actually need to sample as many edges as to be able to say that these things are spectrally close. Maybe what we should be looking at instead is just looking at this expression directly and just look at when it decreases in expectation. Because if the right-hand side, or if this expression, if this distance is just smaller in expectation by a constant factor, then we know we're going to solve the problem quickly, regardless of it being true always. And so Richard put Michael, Rasmus, Anup, and me on a quest of trying to figure out how to bound this term. So actually, the bounds for H inverse itself, just proving that. So what you'd like to prove actually is you'd like to prove that if you sample H by taking a low-squared spanning tree and adding a bunch of edges to it, then for any vector it will be true that it's somewhat close to and you'd like to prove that this extra part, which is H inverse LH, is not too large. If you obtain bounds of this sort, then you can set alpha appropriately, and you're going to know you're making progress. So this is actually not that hard to show. So actually, Richard gave a proof of this himself for some particular sampling scheme, and so what most of our attention focused on was proving this the bound for the second order term, and it was something I worked on for quite a few months, and it was hard. I have, it was actually like one of the first problems I worked on in academia, and it was sort of the first problem I really got to grind my teeth on. And sort of we had a bunch of these attempts based on writing it out and trying to put different inequalities in different places, and maybe something will stick, and it was really proving out to be quite hard. And Michael, who we collaborated with on the construction of search spanning trees before, he started his last year of undergrad at MIT. He, I think, took a break from this problem for a month or two, and then came back. And first of all, he was sort of unhappy with the proofs we had for this. Right? So he didn't really start out thinking about bounding the second order term, which was non-obvious to anyone. But he really wanted to understand these things. So the proofs we had were sort of ad hoc and combinatorial, and he really wanted to get a good understanding of, why we can really expect the inverse of this funny sampled sparsifier to be similar on any vector to the original graph. And so the notation we would typically use then is, if you're only worried about proving these problems, you can just assume that L is identity, which will simplify things quite a bit. So then, we will, okay. So then really what our problem is we have a bunch of vectors. That sum to identity. So this will be this will correspond to edges in our graph, with the property that so they all have stretch less than epsilon with respect to t, which is a spanning tree, but we don't really care. It's a tree here, it's just some matrix. And what we want to prove is that if we take t, and then and let's say they go from 1 to m. What we want to prove is that if we take the tree t and we add random edges from here, we really only has to add a constant factor of them in order to get a good approximation here, which will allow us to recurse. Okay, so Michael's so Michael started out thinking about how to really get to the bottom of this inequality. So trying to understand what happens when you with the first order inverse. And so let's say we have some sample hi that is obtained after sampling I of these edges. So we sample them just let's say it's actually always equal to epsilon for simplicity. So we sample these edges uniformly with replacement. We have some hi, and then we wonder, okay, so how will the expression v transpose hi inverse v change after we add one additional edge to hi? Okay, so first, what Michael said is, imagine instead of adding the actual edge to hi, we add sort of the expectation of what we would add. Right? So the expectation of what we would add is just 1 over m times identity, because we have m edges as sum to identity. Okay. So then proving a bound for this, proving that this is actually smaller than hi is quite simple. And we can actually show that this is yes. So this should be less than 1 over v transpose hi inverse v. And here we'll just have right, okay. Yes. So then we'll have plus m, I believe, minus I'm getting lost a little bit since I'm looking at I'm giving the proof from the unrefined original Michael note from the date of invention, which was refined many, many times afterwards. But I really think the idea he had there was very nice and yields some insight into how he came up with a solution. Anyway, there is a lot of inverses here. OK, but anyway, I'm sure you can believe me, this is not a very hard expression to bound. What is interesting is, and what really was in Michael Worth himself, it was the key idea to his solution is that, so this is what would happen if you add the full edge. And his idea was saying, well, what happens if instead of adding a full edge, I just add I just think of adding it continuously, right? So I start with my sparsifier, and then I add, instead of adding the edge at once, I add it linearly. So he defines the function f of x, where x goes from 0 to 1, as this. So yeah, at f of 1, we know we have made some progress with regards to our original sparsifier. And the idea is that this function f of x is actually convex with regards to x. So it has an increasing derivative, which actually means that because we can bound this expression for x equals to 1, we can bound the derivative of x at 0. So we can actually say that f prime of 0 is is at most f of 1 minus f of 0. Right, and actually, OK. So f of 1, the expression I was missing is actually the harmonic sum, which is a term Michael coined of the previous score and 1 over m. And harmonic sum is just the inverse of the sum of inverses. OK. So this is just and now, OK. And now the very nice part is that so this is the derivative of sort of adding the entire graph to our current graph. But actually, this derivative is equal to the sum of derivatives of what would happen if I took a random edge and added it to my current sparsifier. Right? So if instead of I in this expression, I had only some single edge, and I tried to add that, I tried to add that, and then look at how this V transpose sparsifier inverse V changes. If I'm only looking at the derivative at 0, I can actually say that that this derivative is the sum of those derivatives, which is actually very nice, because if you try to look at these terms directly, so after you take a discrete step, it's pretty hard to say something interesting. So the idea.
1 more minute.
Okay. Yeah. So then we can actually get a bound on we can actually get a bound on H inverse based on that. But there is one very beautiful consequence of this more principled way of looking at this problem, and that is that this f prime of 0 that we are looking at, if you actually compute its value, it's going to be roughly 1 over m times v transpose h to minus 2 v, right? And so we have proved that this thing is is not too large, and we actually know that because this function is convex, we know that if we sum we sum the values of f prime of 0 as we go with hi over a large period, we know that the sum of all these derivatives is bounded by the total progress that we made. And so we can actually use this fact to get a bound on the second moment of our sparsifier. And I think that's really cool, how Michael's desire to just understand the first part, the first order approximation of our sparsifier has led to just solving the whole problem. And if there is any extra time, I might add a conjecture that we worked on with Michael for a lot of the time that we were together at CMU and later, and we have never really solved, but Michael was very excited about it at some time. And that the conjecture is the existence of spectrally supported spanning trees with constant total stretch. So actually, the question, so.
You don't have extra time.
Okay, I don't have extra time, but okay. Okay, well, okay. Thanks.
Questions? Oh, sorry.
What is this conjecture that Michael was saying?
Yeah.
Okay, I guess I use this trick as well.
Yeah, so thank you. So the conjecture is, okay, so we know due to Abraham and Neyman that if you have a graph, you can find a low stretch spanning tree with total stretch of m total stretch of m log n log n. And now it turns out that if you the tree has a fairly strong property in that it's actually a subgraph of the graph. So instead, you might only want the tree to be spectrally supported by the graph, so just spectrally less than the graph as a matrix. So if you want that, it's immediately not too hard to you can just apply any sparsification algorithm, sparsify the graph first, and you can get a tree with total stretch, say n log n log n. And you can additionally use, let's say you can additionally use Steiner vertices. And you can actually prove that you will need Steiner vertices for the full conjecture. So let's say we only want a graph that is spectrally supported by our graph, and it can have more vertices. We just want to be able to sure complement them out in order to get a graph that's spectrally less than our graph. And let's say we want a tree like that. It's very easy to show you can get that tree to have stretch n log n. And the conjecture is that you can get always that there always exists such a tree with total stretch n of O of n. So we had this nice thing going on for a month or two where we would come up with examples, and then mostly Michael would try to find a way of constructing trees for that particular family of graphs. It's a very entertaining source of puzzles. You can come up with all sorts of weird graphs. Yeah. So the conjecture is still unresolved.
And was he willing to bet on one of the outcomes?
I think if he would bet that they exist.
But he didn't bet.
But I mean, I also believe that they exist, so maybe we didn't find anyone to.
Okay, thank you. So there's a reception outside, so you can just chat there.